So in today's video, we're going to go ahead and cover the first fundamental theorem of single variable calculus. And so let's suppose that we have this situation right over here. Suppose that we have some function f of t that's continuous on this interval from a to b, so right over here. And this is kind of just an arbitrary function f of t that I drew out kind of to illustrate the situation. But suppose that we have any function that's continuous on any arbitrary closed interval from a to b, right? And so it contains the endpoints because it's a closed interval. And suppose that we wanted to find, or we wanted to pick some arbitrary x that's located within this interval. So here we have x that's located within our interval a to b, within our closed interval from a to b. And essentially what we wanted to do is we wanted to find the area under the curve from our lower endpoint a until x, right? And x is contained. So x could also be a, x could be b, or it could be any point in between a and b, right? Or any value in between a and b. So suppose we wanted to find this area right over here, right? So what we would do is we would go ahead and we would use, what we would do, is we would go ahead and we would use the integral, right? We know that the integral would give us the area under the curve. The definite integral, at least, would give us the area under the curve. So this would be the integral from a to x. Remember, x is just some value, it's some number, of our function f of t. We're using the variable t because we're using x as our particular value, so we're going to use t as our independent variable, dt, right? So this would give us the area, right? The area beneath our curve over the interval from a to x, where x is contained within the interval a to b. And we know our function is continuous over a to b. It doesn't really matter what else it does outside of that interval. And so the first fundamental theorem of calculus tells us that if we have essentially the derivative with respect to x of the integral from a to x, of the definite integral from a to x of f of t dt, then that is just going to be equal to f of x. So suppose that we define this area under the curve as a function, right? Because x could vary. It could be anywhere from a to b, so it could be any number in between those two endpoints. And so if we define this as some function, capital F of x, right, because x would be our input in this case, then essentially what this function gives us, whenever we put in an x value, it gives us the area under the curve of f of t, of lowercase f of t, from t equals a to t equals x, for any x contained within the interval a to b. And so essentially what happens is if we take f prime of x, so let me go ahead and move this over here, then f prime of x, capital F prime of x, is just going to be equal to f of x, if that makes sense. So f of x, what we do is we just change this independent variable. We change it from a t into an x when we want to take the derivative, right? And so essentially, this is only going to hold true, of course, for all continuous functions f on our interval from a to b, and also for every x contained in our closed interval from a to b. And the reason why this is very important is because it kind of helps us now when we're thinking about the integral. We're thinking about it in a different way now, because we used to think about the integral as purely the area under the curve of a given function. But now what this tells us is that the integral is basically the antiderivative. So if a function is continuous, then that function has an antiderivative, right? And so if we thought about kind of if you want to think like inverse functions, right? If you want to take a function and then apply its inverse, then you end up with the identity. Same thing over here. You take a function, you take the derivative of that function. If you want to kind of undo the derivative, then you apply the integral. And so that's kind of what the first fundamental theorem of calculus tells us, is that the integral is the antiderivative. And so it gives us a new interpretation of what the definite integral is, or what the integral is in general. And let's go ahead and apply this to a particular example right over here, which may look a little bit intimidating. I mean, this actually looks quite terrifying. So suppose we have a function, capital F of x, and it's defined as this crazy integral right over here. So the definite integral from e squared to x of the natural log of t times tangent cubed of t divided by the square root of t to the 7th minus 9 e to the t dt. So this is a very intense, scary looking integral. And what we're asking for here is we're just asking for the derivative of capital F of x, so of capital F prime of x, right? And if we want to just go back to the fundamental theorem of calculus, if we want to go back over here to the first fundamental theorem of calculus, when we have this type of situation, this one right over here, which is in the same form as this integral right over here, then, and we want to take the derivative of this function, capital F, we want to end up with capital F prime of x, we just take whatever this integrand is, right? That's what we call it. Let me remove all these lines. And essentially, we just change the variable. We change the dependent variable, or the independent variable from t, we change it to x. That's basically all we have to do, and then that gives us f prime of x. So let's go ahead and do that. And so this is just going to be the natural log of x times tangent cubed of x divided by the square root of x to the 7th minus 9e to the x. And that would be our final answer right over there. So as we can see, I mean, using the first fundamental theorem of calculus makes our life significantly easier when we're tackling these types of situations. And we're going to come to find later on is this also helps us sort of define accumulation functions a little bit easier now.